Today my topic of discussion is crystal field stabilization energy. Now, some basic background we need to know, like metal and ligand, these two constituents is making the complex compound. Metal complexes are formed by different metal ions like cobalt, chromium, iron, and this ligand is some species which are electronegative or neutral in nature, getting attached to the central metal cation, forming a coordination complex. And the bonds involved in this type of compounds are mostly coordination bonds. There can be covalent bonds, ionic bonds, all sorts of bonds present into a complex compound. That's why we call it a complex compound. If we compare with ordinary the salt like sodium chloride, you have only one type of bond present, that is ionic bond or ionic interaction rather. Whereas in a complex compound you will find all three sorts of major bonds, major types of bonds: ionic, covalent, coordinate covalent, all sorts of bonds present in a single compound, and that's why we call it a complex compound. Now there are certain factors that will that specify whether the strength will be good, the complex will be a stable one or not. Some they are called metal factor and ligand factor. Metal factor means depends on the type of metal. This it will vary. The strength will vary, or the complex compound will have this property. What are the metal factors? Number one is oxidation state. Then number of d electrons. Now let's go one by one into these points. Oxidation state, if you go think about, then if you take a higher oxidation state, more will be the interaction with the ligands. Higher oxidation state will give more interaction. Lower oxidation state will give less interaction. For example, ferrous and ferric. Ferric will give more interaction with the same type of ligand. Ferrous will give less interaction. So that is your metal factor. Now this total 5 d orbitals are present into this metal we are talking about. These d orbitals, these 5 d orbitals, we can divide into two categories. One is some of these d orbitals are in the plane, okay, like dxy, dyz, dzx. They are aligned and along the plane. And some d orbitals are there, actually two in number. They are along the axis. Okay, so like dz2 and dx2 minus y2. So these are along the axis. Now these 3 d orbitals which are along the plane, dxy, dyz, dzx, they are of similar energy. And initially, before any sort of crystal field is created or ligand field is created, that these d orbitals are same energy level. They are called degenerate. Okay, so these 5 d orbitals are initially degenerate. Whenever the ligand approaches, how the ligand is approaching? Along the axis. Okay, so if we go for a octahedral splitting, then the d orbital will be aligned according to this set along the plane or along the your this xyz axis, and this ligand is approaching along the axis. So out of these 5 d orbitals, 3 dxy, dyz and dzx will feel maximum repulsion. Okay, because the no, actually sorry, this is they are forming minimum repulsion, because if you approach along the axis, then the ligand is actually approaching in between the two lobes of the orbital. Okay, just if I show you here, yeah, if I show you here, suppose the ligand is approaching along x-axis, so it is in between the two lobes of the orbital, so repulsion is less. Whereas if we approach along the x-axis in this orbital, then you will find the ligand is approaching along the x-axis and the lobe is also along the x-axis. As a result, there is a very, very strong repulsion. So the repulsion will be very high here, whereas repulsion will be comparatively less here. So these three will give one sort of set of orbitals energetically similar, and these two will form another set of orbitals energetically similar. These three set is called T2G, and these above two are called EG. Now this T2G, it is T for triplet and G for Garrett. Garrett means even. So these d orbitals are even, symmetrically they are called even, and G is Garrett, that is Latin word. Garrett means even. So these d orbitals are energetically similar, they are degenerate, and they are called T2G orbitals. Triplet state, because three different orbitals will form three peaks, so triplet state. If you plot into a electron cloud along the electron cloud against the distance from the nucleus, if you plot, then probability distribution pattern, you find three peaks in this case, because three are energetically same, and here you get two peaks, and accordingly this is called triplet, and these two are doublet. Okay, and these are called T2G, and these two are called EG orbitals.
Crystal field theory explains most of the properties of complex ion bonding. Ligand field theory is actually MO theory applied to complex ions,
Well, so
and is only
in the
briefly
crystal field
considered in
theory,
these
when
tutorials.
the ligands are
The
approaching
idea of crystal field
towards the
theory
central
is
metal
that the
ion,
ligands
some
approach the central
field is
atom
created.
and
That is
create a
called
local
field.
crystal type field,
Along the
and this affects the d orbitals
axis
of the
or
central
along
atom.
the plane, whatever way it approaches around the
Transition metal
ion,
chemistry
then you
is
find
dominated by
there
the
is a
d electrons that can
sort of
occupy the
repulsion
5d
that is
orbitals.
generated.
Here is shown
First of
the
all, no
5d
field, then
orbitals of the free
octahedral
central
field,
atom.
then tetrahedral field.
Also,
If you
the
take
5d
tetrahedral
orbitals
field,
in the
then the
tetrahedral
ligand is
field,
approaching
and
along
the
the
5d orbitals
axis.
in an
But if you
octahedral
take
field.
tetrahedral field, then it is approaching along angularly.
For a free transition
Okay,
metal,
so for
in the absence of any
tetrahedral,
crystal
only
field,
4 ligands
the
are there, and
5d
for
orbitals are
octahedral,
degenerate,
6 ligands
which
are
means that they all have
so
the
when
same
6
energy.
ligands are approaching, you will find that two sets of orbital generated, T2G below
In an octahedral
and EG
field,
above.
6 ligands approach.
So now just
two
look at
along
here
the
in
plus
this.
and minus
So
z-axis,
this crystal field
2 along the
theory
plus
here
and minus
explained.
x-axis,
So here
and 2
these
along the
5d
plus and
orbitals
minus y-axis.
are
When a ligand encounters
yes,
a lobe
see here,
of the
these
central
5d
atom's
orbitals
d
are
orbitals,
getting separated.
it raises the
This
energy.
dyz,
Hence,
dzx,
the
they will
dz
be
squared and the
energetically
dx
higher.
squared minus y
These
squared orbitals,
two will be
which lie
energetically
along the
higher, and
x,
others
y, and
will
z
be
axes, are
comparatively
raised in energies,
lower.
whereas the
So two will
dxy, dyz, and dxz
So
are
this way,
out of the way of the
they are
ligands
becoming
and are
energetically
of
higher,
lower
but not
energy.
that much. These dxy, dyz, dzx, they are energetically
In a tetrahedral crystal
getting
field,
slightly higher,
4 ligands
and
approach
other
along
two are
opposite
energetically
corners of a
becoming
cube,
more.
forming
Now,
a
if you take
tetrahedral crystal field.
tetrahedral,
In this
these-
case, the dxy,
these
the
two,
dyz, and the
Z2
dxz
and
orbitals are
DX2
raised in
minus
energy,
Y2
whereas
will
the
be
dx squared
raised
minus
slightly,
y squared
and
dz
dxy,
squared
dyz,
orbitals
dzx
are
will
lowered
be
in energy.
raised more, and accordingly we get T2G and EG in two different sets. So here it is for yes. So this
In an
is
octahedral crystal field, we
for
say that the d
octahedral, this
orbitals
splitting is
have
occurring,
an octahedral
and
energy
we call it
splitting,
T2G and EG.
and we denote this by
And
a
energy
capital
difference between
delta
the
with a
T2G
subscript
and EG
oct.
is called delta O, octahedral splitting energy. Now tetrahedral, if you consider these two orbitals dx2 minus y2 and
The
dz2 are
tetrahedral
below,
splitting of the d
and
orbitals
other
is opposite
three
to that
dxy,
of the
dyz and
octahedral splitting.
zx are above.
Also, the
So,
tetrahedral
they
crystal
are
field
again
only
called,
involves 4
they are actually
ligands,
getting
whereas the
separated. So this
octahedral
difference
crystal
is called
field involves 6
delta
ligands.
tet. Tet means
Hence,
tetrahedral.
the tetrahedral
So
splitting
energy
is usually
difference
less
is
than
comparatively
the
less than
octahedral splitting.
octahedral. Because in case of
For
octahedral,
the same type of
number of
ligands,
ligands
the
is also
tetrahedral field
higher.
splitting is equal
6
to
ligands,
4
but here it
9
is 4
spans of the
ligands.
octahedral
So
splitting.
accordingly, there is a relationship.
Note that as these
Tetrahedral
splittings
splitting
increase,
energy is 4 by
if
9
possible,
into octahedral
the upper
splitting
electrons
energy.
fall down to the lower states. These two different electronic
if you compare
configurations
the
are called
tetrahedral and
high
octahedral
and
splitting
low
energy,
spin
the
complexes.
tetrahedral splitting energy is
The reason complex ions display such an
less
array of
compared to
colors
octahedral.
is that the crystal
Now
field
the
splittings
depending
lie
on
in
the
the visible spectrum.
the metal, we get
Light
different
passes
colored
through a
complexes.
solution of complex
So you see the
ions,
colorful
which
bottles
absorbs the
is
light
representing the
specific
thing
to that type
that we
of
are getting
splitting,
different
and the
colorful
electrons jump
complexes.
up.
Different
What we
metals are
see
giving
is the light
different
that gets
colorful
through
complexes.
and is not absorbed.
Like we know that copper is forming blue complex cuprammonium sulfate. Then iron, if you make complex, so it will be brilliant red color complex, Prussian blue, Turnbull's blue, which is very dark blue color. So this is formed by iron. So different metals are giving different colorful complexes. Now go one by one, we will go into detail. This oxidation state. So as was a point at the beginning. So if you go for a cobalt ash ion, here the splitting energy is found to be 9200 centimeter inverse, whereas the cobalt eke, ash and eke, the eke one means higher oxidation state plus 3 state is found to be giving a splitting energy of 20760 centimeter inverse. Here the centimeter inverse is not energy, it is wave number, but wave number is proportional to energy. Well, it's because wavelength is inversely proportional to energy, and 1 upon lambda, 1 by wavelength is called wave number. So it is becoming proportional to energy. So higher the wave number, higher will be the energy. So accordingly, this cobalt ash state, the oxidation here, the lower oxidation state, the splitting energy is found to be 9200 centimeter inverse equivalent. Whereas for eke ion 3 plus, the delta O means octahedral splitting energy 20760 centimeter inverse, which is much higher. So ash state and eke state, M2 plus and M3 plus. So in case of M2 plus, here you just see this is M2 plus, the splitting energy is, and M3 plus, the splitting energy. If you compare, this is quite less and this is quite higher. Next point, number of d electrons. If you have more and more number of d electrons, you will have a so here you can compare the two, nickel and cobalt. Here for cobalt d electron is 7 and for nickel the d electron is 8. So more d electron is actually occupying the higher energy state, that is the Eg level. It is filling Eg level more, and that's why the splitting energy is going down. So instead of 9200 we are getting it 8500, and the splitting energy is inversely proportional to the number of d electrons. Why? Because the electron is actually occupying the Eg state, not the T2G. Nature of metal ions. If you go in the periodic table downwards, first you get cobalt, below cobalt you get rhenium, then you have get iridium. For cobalt, the delta O value is 2300 centimeter inverse, whereas rhenium we are getting 34100 centimeter inverse, and for iridium we are getting 41200 centimeter inverse. That means as we go down in the periodic table, the splitting energy is getting increased. Okay, so increase from 30 to 50%, from 3D to 4D it is found. Okay, from 30 to 50% increase from 3D to 4D. Not only the size increasing, but the number of proton in the nucleus is also increasing, and the if you go for a 3D to 4D to 5D, your shielding effect is getting reduced. You are getting poor and poor shielding effect, and that's why the interaction is becoming higher and the splitting energy is increasing. Then the fourth point, spin pairing energy. Metal with higher pairing energy will have lower delta because it will actually reduce the your splitting energy, and lower pairing energy will have a higher delta. It is subtracting from the, that is because the pairing energy is actually subtracting from the that splitting energy values. Now the ligand character. The better the ligand, more will be the field strength. Accordingly, we are dividing into weak field, medium field, and strong field, very strong field ligand, and accordingly it is arranged here. Just see here, iodide, bromide, it is then you have SCN, and highest one is found CO, Cn minus and CO. We have the very strong energy, CFSE value, crystal field stabilization energy value. Why it is so? That is because the cyanide and carbonyl, carbon monoxide here is called carbonyl as a ligand. So here these two are capable of forming back bonding. They have pi star orbital and they are capable of accepting field d electron from the metal atom or metal ion. From the metal ion they can accept electron into their pi star orbital, and that's why they are giving some back bonding or partial double bond character, and as a result these two are giving maximum field strength. Strongest field is found from these two. So weak field ligand will give lower splitting and a strong field ligand will give higher splitting.
Octahedral splitting. Isolated metal with 5 degenerate d orbitals. That is dxy, dyz, dzx, dx square minus y square,
So here
and dz squared.
you can find these 5d orbitals, how they are getting splitted up. Now this is the combined
6 ligands approach the d orbitals
effect. It is seen
along the
6
x,
ligands are
y,
approaching
z
along the
axis from both
x, y,
sides.
z axis from both the sides, and you will
As the
find
ligand approach along the
that
axis,
as the ligand is
dx
approaching along the
squared minus
axis,
y squared,
so dx2 minus y2 and dz2 orbitals are
are
spread along the axis. As they are spread along the axis, you will find more repulsion, and other 3 orbitals, those who are along the plane, will feel much less repulsion, and accordingly the splitting goes.
dzx orbitals are spread,
And the difference in this energy
experience
of
less
this
repulsion
T2G and
due to
EG
interaction
is
with
called
ligands.
crystal field splitting energy or CFSE. Well,
These
these
are
3
T2
are
orbitals.
T2G set, and other 2 above they are EG set, and the energy difference between the 2 is the CFSE. Now energy in terms of number of electrons occupied, if you can calculate, that is actually called CFSE. But in the just the energy difference or the gap, if you measure, it is called delta O, the octahedral splitting energy or tetrahedral splitting energy. It is that way it is mentioned. Now tetrahedral splitting, this T2G, here we are not mentioning the Z, the term Z, because here the garret and ungarret, this barycenter is absent, and that's why this garret and ungarret, these terms are not becoming meaningful here. And so these 2 orbitals dx2 minus y2 and dz2 are below, whereas the other 3 dxy, dyz and dzx are above. Now it is found that this delta SP means it is and delta OCT and delta TET, this square planar, this delta SP is square planar, this delta OCT is octahedral, and delta TET means tetrahedral. Square planar is found to be giving maximum splitting compared to octahedral, which is giving more splitting compared to tetrahedral. This is because of bond angle. Square planar, the bond angle is only 90 degree, and octahedral, these 4 orbitals are there 90 each, and here this octahedral, this is also perpendicular, but there are total 6 ligands, and here in the tetrahedral there are 4 ligands. So octahedral splitting energy is found to be more than the tetrahedral splitting energy, and you can get the total diagram at the bottom. Here, before any splitting occurred, it is called isotropic field. What does it mean? Isotropic field means along any direction the field strength is equal. The splitting is not yet generated, the ligand is not yet approached. So in the situation, it is in the isotropic field. Now the ligand is approaching and the splitting happened. So the CFSE value, it is the ligand field minus the isotropic field, the difference of the two. After the ligand field created and before the ligand field created, the difference is called the CFSE. So this is the isotropic field, and after the splitting occurred, we get the difference here. So CFSE we can calculate according to this formula. This portion, bottom portion is minus 0.4 and the upper portion is plus 0.6 because of energy balance. Here how many number of orbital? 3 into minus 0.4, so it is becoming minus 1.2, and the above these two others two, here you get 0.6 into 2, that means plus 1.2. So here it is plus 1.2 and here it is minus 1.2, so it is getting balanced. So that is coming from the energy balance. Now CFSE, crystal field stabilization energy, is equal to minus 0.4 in N means number of electron, T2G, that is occupying the T2G orbital, plus 0.6 into N number of electron into EG, that is occupying the EG orbital. EG orbitals occupied, number of electron here, so plus MP. MP means M is the number of pair of electrons and P is the pairing energy. So this pairing energy actually getting deducted from the CFSE value. That's why more the pairing energy, CFSE will become lower. Next, if we calculate for tetrahedral value, 4 by 9 into delta O, that is the tetrahedral value. Tetrahedral value is lower compared to octahedral. So for tetrahedral, the CFSE will be calculated like this: minus 0.6 Ne plus 0.4 N T2, but just observe here, there is no G mentioned. Here there is no G. We are just mentioning E and T2 into delta T. Delta T is the splitting energy for the tetrahedral complex. Now here we get delta T equal to 4 by 9 delta O, and that is the relationship. Now according to this diagram, we can calculate isotropic field. So 7 into 0, because these are all in the degenerate state, so they are having no source of energy is there yet, means it is neither reducing energy or decreasing energy. So we are considering this is the baseline. So baseline we are considering 0, so that's why 7 into 0. 7 electrons are all in the baseline, so it is 0. Plus 2 paired of electrons there, because 2 pairs are present. So each we can represent by P. So as there are 2 pairs, so it will be 2P. So isotropic field is 2P. After applying the ligand field, we are calculating like this in the formula. It is getting minus 0.8 delta O plus 2P. Now if we add these two, so it is this ligand field minus the isotropic field, this 2P will be cancelled and CFSE will be minus 0.8 delta O. For a low spin D7 octahedral complex, again we can calculate for another example. Isotropic field, it is becoming 2P. Ligand field, the same formula, it is again octahedral, so minus 0.4 into 6, because 6 number of electrons there in the T2G orbital, so total 6 electrons, so minus 0.4 into 6, plus here there is only one electron in the EG orbital, that's why 0.6 into 1, and how many pairs? 3 pairs. After the ligand field created, how many pairs? 3 pairs, so that's why 3P. So total energy here is minus 1.8 delta O plus 3P, and CFSE will be calculated as ligand field minus isotropic field. So this PP cancel and we get minus 1.8 delta O plus P. So that way, if we calculate octahedral for DN configuration, we can calculate the CFSE for different complexes as according to this chart, and it is taken from a book from the Inorganic Chemistry by Catherine E. Housecraft and Alan G. Sharp. So this is continuation again. Number of d electrons if we change, then how the CFSE is changing, that is given here. Okay. So 5d, if you have 5d electrons, the CFSE becoming 0 because total all the orbitals are getting 1 electron. So 3 in the T2G and 2 are in the EG. So it is giving 0. And if you take total filled d orbitals, 10d electron also you get 0. For 5d electrons it is 0, for 10d electrons it is 0. Spin pairing energy. If we pair up the spin, some repulsion factor is there because of electron-electron interaction. There is some sort of repulsion, Coulombic repulsion, and also loss of some exchange energy. So that's why pairing is some energy demanding process, and it is called pairing energy. Now, loss of exchange energy, how much exchange energy is there due to electron, that is calculated by n into n minus 1 by 2, where n is the number of pair of parallel spin electrons. Okay, here one example is taken for high spin and low spin, just to understand the how much loss of exchange energy is there. So it is here we are taken example Fe2 plus 6 electrons, and how many orbitals? Total 3 are in the T2G, 2 in the EG, and 6 electrons will be paired up like this for high spin. So 1 electron each filled up. So then number of electron is taken as 5. So here it is n into n minus 1 by 2, so that is 10. Whereas for low spin means all the electrons are paired up, so the exchange energy is coming 3 into, because here it is 3 electrons, so 3 into 3 minus 1 into x, so it is 6. Another example, Mn2 plus d5. Now for high spin we are getting exchange energy 10, and because 5 electrons are there, and here low spin 3 electrons are there, and we are getting loss of exchange energy 10 minus 4, that is 6. Low spin will occur if delta O greater than P, and high spin will occur whenever the delta O lesser than P. For weak field ligands, pairing energy will not be considered with CFSE. Whereas for strong field ligand, pairing energy will be considered along with CFSE. We consider two different complex. One is COH2 whole 6 2 plus and COCN6 4 minus. The first one here, it is weak field ligand, and this one is strong field ligand. So here both complex, cobalt is 2 plus 2 oxygen state, same pairing energy, ligand field strength will be considered. So for weak field the pairing energy is not calculated, but for strong field it is calculated. So here for high spin pairing energy is not calculated, and for low spin the pairing energy is calculated. Why? Because in the high spin the electrons are not paired up, and in the low spin the electrons are paired up. That is the reason. Thank you.